Hi grade 10s, this is Learn Extra and we're getting into some chemistry today. The topic of today's session is chemistry and solutions. Now if we look around us, we'll find that water is everywhere. There's a fancy name for that. We say water is ubiquitous. And things dissolve in water to form solutions. Now, solutions are really special in chemistry, and we want to look at what's happening in a solution, how it forms, and we want to see some terms that we're going to use with solutions, how we measure solutions, and how we see what's happening inside them in terms of the particles that are moving around, the microscopic view. We're also going to take a look at some reactions taking place in solutions. So let's just summarize those 3 points, and you can have a look at the key concepts. What we're going to say, we're dealing with solutions, and we talk about them as being aqueous solutions. That means they're in water, and we talk about the idea of an ion, and we'll come to that. Then we're going to talk about electrical conductivity, the properties of these solutions, and we'll look at reactions that occur in aqueous solutions. Now, let's get going by having a look at the formation of solutions. And we're going to look at ions in solutions. And the first thing I thought that we could do is just have a look at an example of the formation of a solution. We're going to define some terms as we do this. So let's go and have a look at what I've got here. I've got some water in a beaker, and water makes up an aqueous solution. Aqua, water. I've also got some solid crystals. They happen to be copper chloride. I'm just going to take a spatula full of these lovely green crystals, and this is a solid, as you can see. It's made up of little particles, and they're held together by electrostatic forces. The bonding inside here is ionic bonding. We're going to dump it into the solution, into the solvent, at least the water, the liquid part, and if we give it a stir, what we'll see is that the little particles start to separate, and the water has changed color. It turns blue. There are still some salt particles at the bottom. They are in the process of dissolving. We say that process is called dissolution. We're going to have a look at what happens at a microscopic level in a minute, but I think we've got enough evidence to see what's happening in that process. Let's have a look at it. Let's define some terms as we remember what we've just seen. We've made a solution. It's now not completely dissolved, but over time it would, and if I had a bit of time, I would show that to you. Now, there are 3 terms. What is a solution? There are 3 things that you need to know. The first is the idea of a solute. In our example, we used copper chloride. And I'm going to write down the formula, copper chloride, like that. We represent it as a solid, so we use little phase indicators. A little S behind it indicates that we've got a solid. That's the solute. It's the thing that was going to be dissolved. Then what about the liquid component? Well, that was water, and I'm going to write down the solvent. That does the dissolving, and the symbol for water, H2O, indicating the phase as an L. Just by the way, if we had a gas, we would indicate it with a G. But we haven't got a gas here, so I'm not going to complicate things, just to mention it to you. Now, when we add those 2 things together, the copper chloride and the water, well, we get a solution. What happens is the copper chloride is bonded ionically. There are copper ions and there are chloride ions, and what happens, the water gets in the way and they separate. We'll have a look at that in a second. But to represent the solution, we're going to represent the ions that are present. And so I'm going to say I've got some copper 2+ ions, and they're surrounded by water molecules. And so I use a phase indicator to say they are in aqueous solution. AQ stands for aqueous. And I'm going to say not only have I got copper 2+ ions, I've got 2 lots, twice as many chloride ions, Cl-, and they are also surrounded by water. So this idea of them being surrounded by water comes about because we have to get a picture of what's happening in the dissolving process when a solute dissolves in a solvent to form a solution. That process is called dissolution or dissolving, but what's happening on a microscopic level, submicroscopic level even. Let's have a look. I'm going to do a small little diagram to illustrate. I'm going to say, in my ionic solid, I'm just going to draw 4 particles. They are in a lattice, a crystal lattice, and they're held together by strong electrostatic forces. Now, my drawing skills are not great, but I think you can see that I've done something there that just needs a correction. There's another one at the back, so I will put that one in. So there we go. We've got 8 little particles. This one's positive, this one's negative, and I'll perhaps color code them. So let's make the negative one pink. That one will be negative. The ones next to each other are going to be opposite in charge. So that one's negative, and this one will be negative. So we've got 4 negatives and 4 positives. Just make sure that you've got that. That's negative. And these ones are positive. So the green ones are positive. The cations are the positive ions. Remember, the word cation means that it's a metal atom that has lost electrons. I'm going to write that down. The word cation means it's a positively charged ion. And the word anion is a negatively charged ion. Now, the reason that dissolving takes place is that what I've indicated between these positive and negatives, these are electrostatic forces. They are forces of attraction. But we know any force of attraction can be broken if there are stronger forces that are going to pull it apart. And this is exactly what happens. If we've put these little particles into a solution and surround them by billions and billions of molecules of water, well, something interesting happens. But to understand that, we first of all have to understand what the nature of the water molecule is. So let's go and have a look at that. We know that water has a chemical formula, H2O. It's got 1 oxygen and 2 hydrogens. The bonds here are covalent bonds. And in fact, this is a polar covalent molecule. We represent that by saying the electrons are not equally shared. At the oxygen end, there's a negative charge formed, and at the hydrogen end, there's a positive charge formed. And in fact, there are 2 negative charges up here. We're not going into that detail. Suffice it to say that we've got a polar molecule. It's a dipole. Polar covalent bond. It's a polar molecule. Okay, because the electrons are not shared equally. So what happens now? We've got a positive little ion in a lattice, and we've got water molecules that are swimming around it. Well, can you see something? Let's have a look here. If I bring one of these close to here, what do you think is going to happen? Well, I think that you're going to get something like this. You're going to get the positive ion attracted to that negative oxygen. That negative oxygen is going to be attracted. And in fact, you're going to get hundreds of little water molecules surrounding that one little positive charge. So this positive charge gets surrounded by water. And I want to illustrate that over here and show you what eventually happens. Because it gets outnumbered, we've got the positive charge sitting over here, and we've got a whole lot of water molecules that sit around it. Water, another water over here, another water over here, and they sit and they're surrounded. Now, can you see that the forces of attraction between the water, if we had billions of these water molecules coming in, they could pull, and the water molecules like to move. So what happens is they pull and they pull and they pull, and eventually they break the bonds. So what happens is that this little guy over here, I'm just going to try and illustrate it by taking those little bonds out and saying this section here, these ones separate. I need to pull it apart. Just give me a second to do that. Select that one, just that one, and it's not coming. So I want you to see that separates. That little region separates, and it becomes an individual surrounded by water molecules. We say it is hydrated. Hydro, water. Hydrated means the ion is surrounded by water. So the process of dissolving is a process of hydration. It's a process where positive ions get surrounded by water molecules, but what happens to the negative ions? Well, they're also going to be surrounded by water. The arrangement of the water molecules is the opposite though. So let's just quickly do that so that you can have a look at it and you can see the process. I'm going to just take a picture further down so that you've got it. What happens when we've got the negative charge? We've got a negative molecule there, a negative ion at least, and it's hooked up to a whole lot of others in the ionic lattice, and we've got water molecules. Now, the water molecules, they surround them like this. The positive ends go to the negative because opposite charges attract. And so this ion, this anion, is also hydrated. The anion becomes hydrated. And so as I showed you right in the beginning, I said to you, here's the equation. And that's what we're saying. This chloride ion is surrounded by water. This copper ion, or these copper ions, are surrounded by water. Now, we can represent that whole process in a chemical reaction or a chemical equation. So I'm going to write it down here for you. We're going to say copper chloride, which was a solid. It has changed, and this process is important. We haven't made any new stuff. We've just separated the ions apart, and so we represent it like this. We say copper 2 plus has gone into aqueous, plus 2 chloride ions have gone into solution as well. This process where ions move apart is called dissociation. Dissociation. Association means that things join together. You form an association, a club. You're associated. You have associates. Dissociation means you move apart. You separate yourself from the members of the community. So that's what's happening during dissolving. Now, there's one little point that I want to make and come to here, and that is that the opposite process happens when we form crystals. If we had to take that solution and we had to leave it in the sun, put it under some heat, the ions would come closer together, some of the water would evaporate. And here's the thing, crystals would start to form. But there's something interesting. Not all of the waters that are surrounding those ions get the chance, get enough energy to escape. And so there's a term that we use for the waters that are remaining in the crystal. Those are known as waters of crystallization. And we represent it in an equation by writing something like this. We say CuCl2 dot, and then a number indicating the ratio for every one copper, how many waters we've got. And I don't know, so I'm going to put an X there, and we're going to say H2O. This number could be 1, it could be 2, it could be 7, and so on. So that's how we represent. So if you see a formula with waters of crystallization, that number will tell you the ratio of number of waters for each of the copper and the chloride, or the copper and the sulfate, and so on. So remember that idea. We can even calculate what that unknown X quantity is. If we know the mass of a solute before and we know the mass of solution, there's a way of doing it. We'd have to do some chemical calculations, but we'll leave that for another day. Now, there is one further thing that I just wanted to mention. We have only been using ionic, this substance here that was our solute was ionic. But we can have other stuff that is not ionic, it is bonded covalently. So for example, something like sugar. If we put sugar into water, then what's going to happen? Sugar is going to form a sugar solution. And we're going to get sugar molecules surrounded by water. This was solid over here, and this is sugar molecules in water. I haven't used the equation there because I just wanted to have a point here. What's interesting is that in this example, there are no ions. Very important to recognize. We don't form ions. No ions are formed. No ions are formed. But if we take something like hydrogen chloride, which is a gas, and we add water to it, then it will dissolve in the liquid to form a new set of ions. The hydronium ion, which is aqueous, plus the chloride ion, which is also aqueous. Now, this process, where there were no ions to start with, that process is called ionization, the formation of ions. It only happens when we are dealing with covalent substances. But as I've mentioned with the sugar example, not all covalent solutes will form ions. And that's just a process of learning and understanding what's happening within the molecule. Usually when the molecule is not polar, then it tends not to ionize. Polar molecules tend to ionize a little bit more. Now that brings me on to the next point, and that is all about solubility. Now when we talk about solubility, what we're saying is that there are some things that will dissolve, undergo this dissolving process really easily. And some things struggle because those bonds between the ions, or the bonds that are holding the molecule together, they're really strong. And they don't want to get separated and surrounded by the water molecules. So we recognize that there are degrees of solubility. Things that dissolve easily, things that are that make solutions, that dissolve. When something dissolves, we say it is soluble. If it does not dissolve, no, then we say it's insoluble. And the reason is that the forces between the particles, the ions in the solution, or the ions in the solute, or the molecules themselves, don't want to get separated, and so they don't dissolve. Okay, so that's one thing. Now, if we've got the idea that we get things that dissolve, things that don't dissolve, we need to be able to measure the difference between that. How do we do that? We do it by using a term concentration. Concentration refers to the amount of solute, okay, and we can measure this in grams or in the standard units for the amount of substance, which are called moles, which we'll come on to in our next session. But just to leave it there, the amount of solute in a certain volume of solution. Now notice it's not the amount of solvent, it's the volume of solution. Now that means that we've got to be careful. We do the dissolving and we make up the solution to a certain volume. The reason for that is that sometimes when we dissolve things, the volume increases, and sometimes when we dissolve things, the volume decreases because of the spaces between the molecules. And so we're not certain. So it's easier to measure concentration in either grams or number of moles per volume of solution. Very important. Now, what we're going to do, we're not going to focus on concentration. It's just a term that I think is important for you to know, and we're going to come on to the definition and using that term in our next session, but it's important for solutions. What we're going to look at now is what have scientists found, what have chemists found over the years in determining which substances are soluble and which are not. And how can we use these? Well, they've drawn up a list, what they call the rules of solubility, or solubility rules. And I'd like to just go through those very quickly, and then we're going to apply them. The first rule, and it's a very important rule for the environment, is that all nitrates, all salts of nitrates and acetates are soluble. Okay, so you can see if you've got a substance that's got a nitrate or an acetate, the ending for an acetate is CH3COO. If it's got that in its formula, then you know it's soluble. The formation comes from vinegar or acetic acid. Okay, all salts of alkali metals. Okay, that's group 1. Group 1. And ammonia are soluble. So the group 1, lithium, sodium, potassium are the ones that we work with usually, but then there's rubidium and cesium and francium. We're not going to worry about those, but those are the 3 that we're going to worry about. So if something is made up of a salt that's got lithium, sodium or potassium in, we know it's going to dissolve. Now, this one is interesting. All chloride, bromide, and iodide salts are soluble, but there's some exceptions, and we really need to learn the exceptions really well. Silver, lead, and mercury 1. Those salts are not soluble, they're insoluble. We're going to come back to this, but just to note that the color of these insoluble salts, silver chloride is white, silver bromide is cream, and silver iodide is a yellow. Lead, you'll see, is white, light yellow, and yellow. Now, those are important observations, and we will use them to be able to identify if we've got one of these halides present when we do tests on particular type of reactions. So they are important to know. The next thing is all sulfates are soluble except for barium. Barium sulfate, insoluble. Calcium sulfate, insoluble. Lead sulfate, insoluble. And silver sulfate, insoluble. The one that we're most interested in is barium sulfate, although calcium sulfate we do see around. It's found in plaster of Paris. What about carbonates? Now, most carbonates are insoluble, except group 1 metals and ammonia. And then the last one, most hydroxides are insoluble, except those from group 1, ammonia, and barium. Now, that list of solubility, 6 little rules that you need to know, are going to be really useful when we start to do tests on solutions and look at the chemistry of what's happening in solutions. Let's go to a couple of questions now and see if we can use those and make some predictions. Question 1 of our example question says, for each of the following, write a balanced chemical equation for the process when they are dissolved in water. So we're making aqueous solutions. Sodium chloride. Now, what do you remember from the solubility rules? We know all chlorides are soluble except for lead, silver, and mercury. So sodium chloride, all salts of sodium are soluble. So we know that sodium chloride, which is table salt, yes, it dissolves. How are we going to represent that? Well, let's do it. We're going to write the equation first of all, NaCl, for the solute. Now, we must put in the phase. It says that's a solid. We're next going to say it is ionic. So it just separates into forming ions. It doesn't actually use the water. The water is simply surrounding it. So the water doesn't change, so we write it like that. And we then say we've got sodium ions that are hydrated, and we've got chloride ions that are surrounded by water molecules as well. And there's our equation. It will dissolve. It undergoes the process of dissociation. Let's go to the next one. Now, here we go. What have we got here for number B? I'm going to write it down over here. We've got carbon dioxide. We're going to say CO2. Now, carbon dioxide is usually a gas at room temperature, so I'm going to write it like that. What do we know about carbon dioxide? It is covalently bonded. It's a molecule. It's not ionic. So it will react with the water and change the water. Now, we know that carbon dioxide isn't all that soluble. Well, we've seen it. In fizzy drinks, you can see the bubbles of carbon dioxide rising to the surface. You shake up a bottle of your favorite fizzy drink, carbonated water, and you will see the bubbles bubbling up to the surface. They're not dissolved, but there is some carbon dioxide dissolved in that water, and we know that if we heat it, we'll get a huge amount of gas coming off. So some of the carbon dioxide does dissolve, but not all of it, depending on the temperature. Now, when it does dissolve, what does it do? It forms a different substance. So what we recognize here is that it goes to form the carbonic acid molecule, written as H2CO3. Now that's surrounded by water, so we say it's aqueous. And we put in the phase indicator for the water as well. But now something interesting happens. The carbonic acid molecule doesn't like to stay totally as a molecule. Not all of the molecules do this, but some of them, small number of them, break apart to form hydrogen ions, which are in aqueous solution, plus bicarbonate or hydrogen carbonate ions. And they're also in aqueous solution. And this is why we get acid rain forming. We call this second process here ionization. And it is a reversible process, so we can get them forming like that, and we indicate it as reversible. Right, let's look at the next one. Number C, we're going to be looking at the reaction of ethanol in water. What happens? Well, we should know that ethanol, which is C2H6O as a liquid, when we add it to water, it simply forms if that was liquid water, it simply forms C2H6O in aqueous solution. There's no chemical reaction. There's no ionization here. The bonds inside of the ethanol are too strong to break apart, and there's very little ionization, but it does dissolve. So the water is sometimes not even included in that reaction. We're just saying that it goes from a liquid to an aqueous solution. And then the last one, which is a very interesting one because it's dealing with lead to carbonate. Now, you should know that this is insoluble. All carbonates are insoluble, and lead is a particular one that we know is insoluble. So how are we going to write that? We're simply going to say the following. We're going to say lead to carbonate, which is a solid, stays as lead to carbonate. It's going to form a precipitate at the bottom of the beaker. You would get a layer of lead carbonate, white stuff that is sitting there, not dissolving, and then the water on top of it. We would say that's a precipitate. It's sunk to the bottom, and it forms at the bottom. It hasn't formed because it's made a new stuff. It's just gone, and it's insoluble, doesn't dissolve. There's no reaction taking place here, no reaction. Okay, I think it's time to move on to our next one. We'll just do question 2, and this one is really quite straightforward. We just change the color of the pen. We say hydrogen gas, hydrogen chloride gas dissolves in water, name the process. So, and then it says write the ionic equations showing all the states. And why can we say that dissociation did not occur? So I'm going to recognize that this process is called dissolution, dissolving, dissolution, or we could say that it's ionization. We'll show you why that's the case by writing the ionic equation. We say that we've got HCl gas, and we've added to liquid water, and it's going to form these ions plus that are one hydrogen from this hydrogen chloride joins onto the water to form H3O plus, and leaves behind for us the Cl minus in aqueous solution. And there we go. We've got the formation of ions, and that's why we can say it's either ionization or dissolution. The dissolving process is called dissolution. The chemistry part here, we would say, is ionization. The reason that we say it's not dissociation is because we're forming ions for the first time. Okay, I hope that's given you something to think about. We've just been talking about what's happening in solutions, the formation of solutions. Now we're going to go to a short break. After the break, we're going to come back and have a look at some interesting ideas about the conductivity of solutions. So join me after the break. Welcome back, grade 10s. We are doing Learn Extra today, and we're looking at the chemistry of solutions, or the chemistry taking place in solutions. So far, we've defined what a solution is and some of the processes happening at a microscopic level, submicroscopic level between the ions. Now what we're wanting to look at is what these solutions, how can we measure how effective they are? How many ions they have? Now, what I need you to know and to take note of and remember is that whenever we've got ions that are able to move, then we can get a electric charge moving in a solution. So let's have a look at water first of all, and take a look at this topic of electrical conductivity. We're going to come back to some terms, but the first thing I want to do is to say, if we've got pure water, then we'll have a whole lot of molecules that are in the solution, and they will join together in different ways because we know that they are polar. There are intermolecular forces, forces between these molecules that are keeping them together. But if we were to put some electricity or put a power supply into this solution, guess what? These molecules of water don't like to move terribly much. This tells us that we have got mainly molecules. Water, pure water, has got very few ions. And so pure water is a poor conductor or insulator. It doesn't conduct. Poor conductor of electricity. The reason is because we've got few ions. Now, in the same way, I mentioned to you earlier that if we took a sugar solution or even a solution made up of ethanol and water, what would happen? Those molecules are covalent. They aren't terribly polar. They don't make up big charged particles, and they're not free to move. So if we had a solution, a sugar solution, and I'm going to draw the sugar molecule just as a pink dot like that. Say we've made sugar solution and we're surrounding them by water molecules, lots of water molecules around them, something like that. I'm not going to draw lots of them, but just so that you can see that these are in fact surrounded by water. There are no free charges present in the solution. So this is an example of a sugar solution. And what can we say? If we test it, we put some electrodes into it, we're not going to find this being able to conduct. It doesn't have ions. It's not able to conduct. So there are no ions or very few ions, and so it's a poor conductor. Now, what's different about a substance that's ionic? So if we take an ionic solute, something like sodium chloride, simple salt, and we put that into water. Now look what the picture looks like. Looks a little different. What we've got is we've got positive ions and we've got some negative ions, same number, and they are swimming around in the water and they are surrounded by water. So they are surrounded, they are hydrated. But if we put an electrode into this solution, connect it to a power supply, and we make this end positive and that end negative, what do you think is going to happen? Think about it for a minute. Well, it's not difficult to see that the positively charged substances are going to move towards the negatively charged electrode. The negatively charged particles, they're going to move towards the positively charged electrode. And so we get this movement of ions. There's a movement of ions. And so we say it's a good conductor of electricity. So different solutions have different measures of conductivity. We can see that they all dissolve. So sugar dissolves, but it's a poor conductor because of its makeup, because it's molecular. Ionic substances dissolve. Yes, they are able to dissolve, some of them. In this case, sodium chloride. But if we had to take an insoluble salt, no, it's not going to conduct because it's tightly held. These ones, dissolved in solution, good conductors. Now, that group of substances that are both soluble in water and are able to conduct electricity, we give them a name. And they are extremely important. These are called electrolytes. They are solutions that conduct electricity. Okay, so electrolytes. We have them in our body. It's the reason our nervous system works. It's the reason that we have got a whole lot of things happening around us. If you go on a marathon and you're going to do some exercise, they tell you you need to replace your electrolytes. If you don't, you will get cramps. And that's the important part of electrolytes. We use electrolytes in batteries. We use electrolytes all over the place. There are special solutions that conduct electricity. Very important for us to know. Now, let's go and have a look at a question based on what we've just done. And we're told here that during an investigation, just highlight the key points here, distilled water is used as a solvent for a number of solutes to determine the relationship between the conductivity and the nature of the dissolved substance. A learner dissolved the same mass of sugar, table salt, hydrochloric acid, and alcohol using water as the solvent to make up 100 milliliter solutions. So we've done it right in terms of the solutions are all 100 milliliters. We've added water to make that up. A circuit was set up as shown below to determine the conductivity of each solution. Now you could easily get this. As I've illustrated previously, we have some conducting rods. There's our solution. There's our battery, and there's a light bulb. Now, the first thing that we're asked is to give 3 constant variables in the investigation and state how each of these can affect the investigation. Now, we've tried to be quite careful here in making sure that this situation is kept constant, that it is a fair test. When they ask you for the constant variables, we need to think about these. The first thing that I can see is that you're going to use the same potential difference, the same cells or power supply. same potential difference. Okay? If you had to increase the amount of electrical energy, you would make it easier, or it would be, make it giving more electrical energy, make it easier for things to move through the solution. So we need to make sure that we've got the same number of cells. The other thing that affects the movement of ions that will affect the solution is we've obviously used the same apparatus. I'm not going to go into that, but we've used the same volume of solutions. And we could also say we've used the same mass. If we had to put more mass or different volumes of solution, we could get different conductivities. We'd get different space for the ions to move in. So we need to keep that the same. The third thing that I think is a really important one that is not obvious, we must keep it at the same temperature. You know that if we change the temperature, we're changing the kinetic energy of the molecules. So keeping the temperature of these solutions the same is really important. So I've just listed 3. There are probably some more that you could think of, but each of these are kept the same. We've obviously kept the size of the electrodes the same, the size of the beakers the same. All of those things could influence the experiment. The same light bulb. All of those, as I said, could influence the experiment. But what are we testing? Let's go and have a look. What is the independent variable? Well, remember, an independent variable is the one that you control. So which is the one that we're controlling? It's the type of solution. So we're looking at the solute that has dissolved, the solute used. All of those are different. The solution, the volume of the solution is the same, the solvent is the same, all of the other things are kept the same. But the type of solution is different because we're looking at the relationship between the type of substance and conductivity. How are we going to measure conductivity? Well, that's going to be in the dependent variable, the one that we don't change, the one that we're not affecting. And how are we going to measure that? Well, what is the dependent variable? It's the brightness of the light bulb. We are not using a meter here. We are just simply using a light bulb in the setup. That's the light bulb. If it's a good conductor, light bulb will be bright. If it's a poor conductor, light bulb won't shine. So now what we're asked to do is to write an investigative question. This is a question where we're going to relate the independent variable to the dependent variable. And we want to know the following. What type of solutions will cause the light bulb to shine brightest or dimmest? Okay, so that's our question. That's what we're curious about. That's what's great about science. We can ask these interesting questions about, well, why is that? If we just put distilled water in, well, distilled water, not many ions present, going to be an insulator, poor conductor. We add some ions, becomes a conductor. So why is that happening? We've tried to explain it. Now let's have a look at the next part of this question. Same setup. It says, explain why we use distilled water in the investigation. And this is one of those control variables. We use distilled water because we don't want to have extra ions, no other sources of ions. You see, if we didn't use distilled water, ordinary tap water can contain chloride ions, it can contain fluoride ions, and those could give us a false result. We could say it's the alcohol that's conducting, and it's not, it's in the water. We don't want to get that sort of false result. So, next thing, which solution does not conduct electricity? Let's have a look at what those solutions were. We recognized we've got sugar, we've got hydrochloric acid, and we've got some alcohol. So which ones, and we've got table salt, which solution does not conduct electricity? Well, there are two options here. The sugar certainly doesn't form ions, not going to conduct, and the alcohol will also not be a conductor. The alcohol might have some small positive and negative ions in it. It's very few of them for some very important reasons. We're not going to go into it. If you gave either of those answers, I'm sure you would get those right, because those are molecules, as we've explained previously. Now, the next one says, predict in which solution the light bulb will shine brightest. We want to answer our investigative question. And so here we've got a situation. We've got table salt and we've got hydrochloric acid. Now, between those, they will form ions. So I just want to take a note of something here. We've got hydrochloric acid and we've got some table salt. Now, the question here is a little tricky, because we know that we're going to form ions over here, like that, and we're going to form ions like that. So sodium ions plus chloride ions. And the real problem here is that in both solutions, we've got lots of ions present. And it's kind of a trick to say, where have we got more? And that's the interesting question. Now, remember what we said. We've got the same mass of the solute. So what we recognize here is we've taken a mass of solute. We don't know what that mass is. It could be 1 gram, it could be 2 grams. But now we've got to work out in which of these substances are we going to get more ions. The way we do that is to say, let's compare their relative masses. And the only way to look at that is to go to the periodic table and to say, well, we know that hydrogen has a mass on the periodic table of 1 atomic mass unit. We know that chlorine has a mass of 35,45. I'm going to round it up to 35,5. And sodium has a mass of 23. So if I was using the same mass of stuff, I want to find out which molecules, which original solute, I'm going to have more stuff in a certain mass. So I want to work out what the overall mass is of the hydrogen chloride and of the sodium chloride. So I hope you can see that this one together, the hydrogen chloride, is going to just be 1 plus 35. That's going to be 36,5. Whereas the sodium chloride is a much bigger molecule or bigger substance. The chlorine and the sodium together, it's going to give you 58,5. So relatively, this one is smaller, less mass. The individual has less mass. So if I take a solution, if I take a sample, at least, not a solution, of the solvent, and I'm saying I've only got 5 grams, where am I going to fit more small particles into? Is it the particles of the hydrogen chloride or of the sodium chloride? Well, the sodium chloride molecules are big. They're going to need fewer of them to make up that mass. So it's a little bit of a trick question to recognize that in the same mass of solute, you're going to get more ions of of hydrogen chloride. You're going to get less ions of sodium chloride. What does that mean? If you've got more ions, they're easier to move, there are more of them, they can get a bigger movement of charge. What's going to happen? The light bulb is going to shine brighter. So my answer to this question, if you had to say that it was either HCl or sodium chloride, at grade 10 level, I think I'd give you the answer. But the most correct answer is to say HCl would be the brightest, because it's the smallest molecule of those two, and there are more ions. There are more ions, it will be brightest. Okay, so it now goes to the next question, and it says, when a container of distilled water is left open and left for a while, it can't be used as distilled water anymore. Explain why. Well, water is this universal solvent. It not only dissolves solid things, but it dissolves gases. And gases like carbon dioxide can dissolve in water. So on the surface, we've got all sorts of gases floating around in the atmosphere. We've got some sulfur dioxide, we've got some oxides of nitrogen, we've got a whole lot of stuff. Any of those impurities can dissolve in an open container of distilled water, and now you've got ions. It's no longer pure. Will be a conductor in a very short time. And if that happens, we can actually even say this is the reason for the formation of acid rain, and that affects our environment. So pure water, because it's such a good solvent, it will dissolve gases and will then become impure. Okay, now I think that we've dealt with conductivity, although quite quickly. We want to move on to our next section, which is looking at the types of reactions. But before we do that, let's go to another short break. We'll be back after that break. Hi grade 10s, welcome back from that short break. Now we're into the last session on chemistry and solutions. We're going to be looking at the types of chemical reactions that occur in solutions. There are many. The reason that the sea is salty is because of a chemical reaction that takes place in solution. The reason that you can run and not get cramps is because of chemical solutions taking place, or chemical reactions taking place in solutions. And so this section, we're going to try and classify some of those reactions, and we're going to use them to identify what else is in a solution. So there are lots of analytical tests, ideas of chemistry, of being able to work out what exactly inside a solution. We're going to have a look at those. So the three types of reactions we're going to look at are firstly precipitation reactions, then gas evolving reactions where we get bubbles of gas, and a very short section on redox reactions. Now, what I want to do is begin by looking at precipitation reactions. So let's have a look at those. Now, what we'll recognize is that in precipitation reactions, we take two soluble solutions, where salts have dissolved, we join them together, and we get a precipitate, an insoluble salt at the bottom of the container. Let's have a look at one. Okay, I'm going to take this beaker over here and this test tube over here. This one's got a particular solution in it. This one's got a solution. You'll see that they're not a precipitate. And if I pour from the test tube into the beaker, watch what happens. I get a cloudy, milky solution forming there. And if I leave it for long enough, it will sink to the bottom. We say that we have a precipitate. Now, what exactly was happening there was that I've reacted two things together. They've exchanged ions. They've gone through what we know as an ion exchange process, and they have formed an insoluble salt. So when we look at precipitation reactions, the key word here is ion exchange. We've got two solubles and we get left off with a precipitation, as we've said. Now, why is this useful? Well, it's useful because we can use them to determine what's in an unknown solution. If we think that we've got a halogen, a halide ion present, we can construct, using the solubility rules, some tests to have a look and see if we've got that particular halide present. I'm going to go through the tests with you very quickly just to illustrate them. For halide tests, we've got tests for chlorides, for bromides, and for iodides. And the simple thing is if you suspect one of those is present, then what you're going to do is you're going to add a few drops of silver nitrate. In the case of a chloride, a white precipitate will form. In the case of the bromide, a slightly cream precipitate will form. And the iodide, we should get a yellow precipitate. Let's see if we can have a look at those. Right, I have in this test tube some silver nitrate. In this one, I have a chloride, then a bromide, and then an iodide. I'm going to add just a few drops. Normally, we would only use a little test tube dropper, but I want to get the picture quite clear. That was the iodide, there is the bromide, and there is the chloride. And you can see the range of colors, from white for the chloride, the creamy color for the bromide, and the yellow for the iodide. Gives you a good sense of, if you get this sort of solution, we're using distilled water, we've only got those ions present, we add some silver nitrate, we're going to get a particular precipitate that we can identify. And so we can say, yeah, we know, yellow precipitate, we've added silver nitrate, we know that an iodide is present. And so that's the test for the halides. Now, what about the sulfate? The sulfate, we use something slightly different. We know that a barium sulfate forms a white precipitate, is a white PPT, the short form of the word precipitate. So if we add some barium nitrate or barium chloride to our solution and we get a white precipitate, hey, bingo, we know that we've got a sulfate present. So if we get this, then we know that we formed a sulfate. Good. Let's go and see if we can get that happening in our rack of test tubes. This is my barium chloride. Here is a test tube containing a sulfate. Let's see what happens when I add the two together. And there we go. We get a white precipitate, and it's very clear that it's not going away. It will settle to the bottom. The original reaction that we did earlier with this beaker was doing exactly the same. So where we add barium chloride or barium nitrate to a suspected sulfate, we get a precipitate. We know that we've got a sulfate present. But there's a little catch, because not all precipitates there are some other precipitates that form with barium. And you should remember from the solubility rules that barium carbonate is also insoluble. Barium carbonate, it's insoluble and white. So we've got to do a little trick here. If we get a white precipitate, to confirm that it isn't a carbonate, we've got to just simply add acid, and preferably some nitric acid, because we know that all nitrates are soluble and we don't want to be adding salts that could form some other. We can also use, we don't want to add sulfate, we could also use hydrochloric. So if it is a carbonate, what will happen? Then we will release some carbon dioxide. Bubbles will be released, and the precipitate will disappear. Now, let's have a look and see what we can do with that. I've got some acid over here, some hydrochloric acid, and I'm going to add it to the beaker and see if the precipitate will disappear. In this case, precipitate, white color, remains exactly where it was. There's nothing that's going to happen in this solution either. So by adding the acid, we've confirmed that in this test tube and in the beaker, we have a sulfate. And so you can see this sort of chemistry is like doing a little bit of a puzzle. And so we're going to look at some questions just now on applying our solubility rules and these tests to work out exactly what's happening. But before we get to those questions, let's go and look at the other type of reactions that take place. And the next one is solutions in which gases are evolved. And so we get reactions where they produce gases. There are two common types of gases produced. There are others. The ones that I think are most common, the ones that you will come across, are where we produce carbon dioxide and we produce hydrogen. Now, if we want to test the gas coming off, we can take carbon dioxide and we bubble it through some clear lime water, and it will turn milky. If we want to test for hydrogen, then what we will do is we will ignite it and we will get a popping sound. The gas will go pop. And so here are ways in which we can test the gases coming out of a solution. I want to show you two examples of gas evolving reactions. So I'm going to move these ones away, and here's the first one, which is really quite common, and you will recognize it. If we simply take a little bit of powder that's for indigestion, and we're producing gases. That bubbling is called effervescence. We've added a solute to the liquid, and we've got a bubbling. But now, it doesn't have to be a solid added to the solution. We could take two solutions. Let's have a look at an example like that. And I'm going to take these two big beakers. And what I want to do here is just to show the bubbles. I'm going to put some dishwashing liquid into one of them. And let's see if we can get some bubbles going. Pour that in. Leave it for a bit. And there we go. We're getting bubbles of gas forming. There are little bubbles for the dishwashing soap formed up there. We made it a little bit stronger, more concentrated. We might have got even more gas, but it will bubble away and it evolves a gas. These are happening in solution. So you can see that the chemistry of solution reactions is really quite a lot of fun. Now, there is one last type of reaction, and I'm not going to go into this in too much detail, just simply to say that it's called redox. And redox reactions are reactions in which there is a transfer of electrons. The most common of these, that are the easiest to see, is if you take a reactive metal and we take a solution of a less reactive metal, what will happen is there'll be an exchange. So, for example, if we take magnesium and we add it to some copper chloride, now in that solution we know that there are copper ions, copper 2+ aqueous. What's going to happen is the magnesium is going to say, hey, I want to give you some electrons. And so it's going to donate electrons. It's going to donate 2 electrons. And the magnesium is going to become magnesium 2+. And the copper is going to gain those electrons and form copper metal. And so we can write the overall reaction as follows. We can say magnesium plus copper 2+. Let's put in the phase indicators, solid aqueous, going to form magnesium 2 plus in solution now, plus copper, which is a solid. Let's have a look at that particular reaction. It will take a little time, but we'll see we've made a solution of copper chloride right at the beginning of the program, and I want to show you what happens when we add magnesium to it. So there's our copper chloride, and you'll see it's a lovely blue solution now. Everything's dissolved, and here I've got a strip of magnesium. Just pull off the surface layer, and you can see it's a shiny silvery color, gray color. If I put it in, what's going to happen? It sinks to the bottom, and after a little while you'll see that it floats, and it's got little bubbles coming off it. I'm going to leave it there for a bit longer. What will happen is that there will be a coating of a reddish color on that surface of that magnesium. As it's going around, we'll see a little coating forming in a few minutes. And what do you think that red-brown coating is? Ah, it's the copper metal. We'll take a look at that right now. Right, notice the color of the solution is changing. It's not as blue as it was before. And if I fish out the little piece of magnesium, I can see that there are tiny little marks that are forming on here that are a little brown color. This tells us that a redox reaction has taken place. Right, wasn't that great? So you can see that there are these different types of reactions taking place in solutions. What we've got to make sure of is that we understand and can balance equations, we can describe what's happening. And the most important ones we're going to focus on in our questions are the ones to do with precipitation reactions. Let's go and have a look at these. So our question says the following. It says, we've got some salt solutions are mixed together. Give the formula for the ions present in each solution before they are mixed, and then write the ionic equation for each when mixed. Okay, so the first one, we've got some sodium iodide and some silver nitrate. I'm going to put the ions present in the solution. I'm going to say I'll have some sodium ions. I'm going to have some iodide ions. I really want to get those silver ions in. And I'm going to have some silver ions here. They're aqueous, they're dissolved. And I'm going to have some nitrate ions. They're also aqueous. Now, what's going to happen when we mix these together? That's in beaker 1. This one's in beaker 1. That's in beaker 2. So they're separated at the moment. What's going to happen when we mix them? Look what's going to happen. They're going to bump into each other. So when a silver and a nitrate bump into each other, does anything happen? Well, let's go back to the solubility rules. What do we know? All salts of silver and all nitrates are soluble. No precipitate will form. But watch what happens next. If we take some silver and it happens to bump into an iodide, yes, we're going to make a new substance. We're going to find that this is insoluble. So this is insoluble. And we're going to make some silver iodide. Remember, that is the yellow precipitate, which we've seen just now. So how do we write the equation? We're going to write it, the balanced equation as follows. We're going to write it down here. We're going to say, let's take some sodium ions. We write it because it says ionic, so I must write all the ions in, plus iodide ions, plus my silver ions, plus my nitrate ions. They're also in aqueous. And what are they going to give me? Well, they're going to give me the following. They're going to give me some, first of all, the precipitate, silver iodide, which is a solid yellow. You can even write underneath there, yellow. And what else is it going to give me? It's going to give me some sodium ions, which are still aqueous, and nitrate ions, which are still in solution. Right, we've got it. That was the overall reaction and the ions put together. Let's go and have a look at the next one. Over here, we've got magnesium and barium chloride. Now, magnesium and barium chloride, let's do the same process as we did before. We're going to say in magnesium, we've got a sulfate solution, we've got magnesium ions, and we've got sulfate ions. And we've got barium ions in beaker 2, and we've got chloride ions. Don't write it as Cl2, that's incorrect. It's Cl minus, not the gas, chlorine. Okay, what's going to happen? Where are we going to get the combinations? I hope you can see that it's that combination that's going to give you your precipitate. I'm going to go right down to the bottom and write down the equation, because I'm going to say I started with some barium, which was in aqueous solution, plus my chloride ions, and there were 2 of those in aqueous solution, plus magnesium, 2 plus, aqueous, plus sulfate ions. Okay, 2 minus. What was my product? Well, can you see we've identified that barium is going to link up with sulfate. So my product is barium sulfate, the white precipitate, plus the other 2 that aren't going to link together. They're going to remain in solution. So it's magnesium 2 plus in aqueous solution plus 2 chloride ions also in solution. Just check that you've got it balanced. Remember, barium chloride was BaCl2. That's why there's a 2 in front of the Cl minus and 2 in the product as well. Now, those are spectator ions. We sometimes don't even include them because they're not really involved in the reaction. What I hope you can see is that there's an ion exchange. There's a swapping of partners. Okay, that was number B. And we're going to need some space for number C as well. Number C is an interesting one because what we've got here is that we've again got barium chloride. So I'm going to just put down the barium, 2 plus, in aqueous solution. Remember, all chlorides are soluble except silver, lead, and mercury. 1. Now, what about sodium? All sodium ions are soluble. Salts of sodium are soluble, but notice from the equation I have 2 of them, so I must put a 2 in front of that, and I must recognize that I've got carbonate ions, CO3 2 minus. Okay, what's going to happen? We're going to swap partners, and when we swap partners, we're going to see that the barium and the carbonate are going to get together. So can we write the balanced equation? Yeah, you can do it. And I'm sure you've got it sorted by now, but let's just write it out very quickly over here. Number C, we're going to say we've got barium 2 plus, that's in aqueous solution, plus the chloride, which was 2 minus aqueous. Was it nitrate? No, it was chloride. It's fine. Plus my sodium, there were 2 of those, aqueous, plus my carbonate, which was 2 minus, all aqueous. Now, what's going to happen when I do the crossing over? We recognize that we're going to form a solid, a precipitate. When barium bumps into carbonate, it's going to form barium carbonate, which is a solid. And what's going to be left over? Well, you're going to be left with the 2 sodium ions in solution. Nothing much happens to those, and the 2 chloride ions in solution. If you wanted to, you could filter off the precipitate and then evaporate the water, and you would be left with sodium chloride. Now remember that if we wanted to confirm that this was a carbonate, we would add acid. The acid would react with the carbonate, and it would evolve some carbon dioxide. The precipitate would disappear. So we wouldn't have a precipitate any longer. Right, I think we've got time to look at the last one very quickly over here. hope you can see that you've got lead ions, and critically, you've got sulfate ions. So the lead and the sulfate ions, they're going to join together, exchange partners, and we're going to be able to recognize that we've also got potassium and nitrate. Potassium nitrate, very soluble, but the lead sulfate is going to give me a precipitate. So what about the final equation? Number D, here we go. We're going to take lead, and in that case it was lead nitrate, so it's Pb2 plus aqueous plus NO3 2 minus, minus at least 2 of those, also in aqueous solution, plus some potassium ions, and there were 2 lots of those, they're in aqueous solution, plus my carbonate, sulfate ions, beg your pardon, that was sulfate ions. Just check it. Sulfate, correct. My sulfate ions in solution. What's going to happen is these ones, they're going to join with the lead to give me a precipitate. So my product is going to be lead sulfate plus 2 potassium ions in aqueous solution plus 2 lots of nitrate ions in solution. Great. We got through that question, and I hope you can see how we're applying the solubility rules here. We've remembered the rules of solubility. You need to write them down. You've got them in your X sheets. Learn them. Make sure you can use them, because in our next question, we're going to apply that very knowledge. So here we go. Question number 5 says, Peter suspects that a sample of water, probably just tap water, may contain either chloride or sulfate ions. How is he going to determine the difference between them? Well, the question says, list the chemicals and equipment that would be needed to test for the presence of chloride ions. Well, we simply need some silver nitrate. We're going to need that. Make sure it's in distilled water. And we're just going to need a test tube, a test tube of the sample. We add the one to the other, and we will see if we get a precipitate. If we were doing sulfate, we would need barium chloride and some test tubes, a test tube of the sample. You could also include in the equipment list the fact that you're going to need droppers. Now, what you would do is you would simply add drops of, for the chloride test, you would add some silver nitrate, few drops, and hopefully you would get a precipitate. If it's a white precipitate, then you know that you've got a chloride ion. Now, we've done the equations in the previous example, so I'm not going to write those equations out. You can check those with your teacher. What about the sulfate ions? Well, simply we would add some barium chloride or barium nitrate, and we will get a white precipitate. But we need to be careful here. That white precipitate, we need to add some hydrochloric acid or even some nitric acid to check that it's not a carbonate. If it remains, then it's not a carbonate. Okay, we're zooming into the last part of this question, and it tells you some interesting observations. It tells you, first of all, that he observes that no precipitate forms when he adds silver nitrate. So what can we deduce? However, a white precipitate forms when he adds barium nitrate. So we can say it's not a chloride. Okay? It's not a chloride or an iodide or a bromide. We know it's not a halide. What could it be? We could suspect that it could be a sulfate or a carbonate. And that's exactly what Candace suggests, that the precipitate may be barium carbonate. What can you do to show her that it is not true, that it is in fact a sulfate? Well, we simply add some acid, we add some nitric acid, or we add some hydrochloric acid, and the precipitate will remain. Okay, well, that brings us to the end of solutions, chemistry and solutions. I hope you see how this is really practical, and it's really quite fun to solve these problems using the solubility tests and the tests that we've described. Take note of it. It will come up in the exam for sure, but all the best. Bye for me.